Howdy, everyone. Welcome to our first class in April. We missed April Fool's Day last week, but I hope you had a nice weekend, whether you did it with a chocolate Easter bunny or jelly beans or some other way. You should have all seen that the exams are graded and you can check your scores on eCampus. I also emailed everyone a distribution of the grades, and that should be right here. The grades were more or less as I might have expected. We had less points on this exam than I've had on some in the past, so the numerical scores go lower for each category, A's, B's, C's, and so on. One thing I want to mention, after we have our third exam, we're going to total up all the scores, including attendance scores, problem sets, and anything else that we might have. And approximately 15% of the class, those with the highest grades, will not have to take the final exam. They can just receive the A grade. Also, I've noticed we have quite a few people that are graduating seniors. I don't remember if it's 2 or 3 dozen, but quite a few. What I want to do is give all the graduating seniors an option to keep the grade that you have after 3 exams, if you want. Obviously, if you have an A, you want to keep it, but whether you have a B or C and you're happy with it and don't want to study for the final, that would be fine also. I'll go ahead and put that into an email at some point, maybe after the third exam or so on, when you know what your grades are. If you have any questions on the grading, please email Dallas. He didn't grade all the problems. Connor graded some, but if there's a question on one that Connor graded, then he can pass it on. And if you're not happy with the response you get from one of the graders, you can go ahead and email me with questions about the grading. Okay, so we're roaring towards the end of the semester, obviously, this being April, and we've already taken care of January, February, and March. So today I hope very much to be able to finish talking about electronic spectroscopy. And then the last topic we'll cover is statistical mechanics. There's some notes in your lecture notes on kinetics, and I hope at some point you'll have a chance to look at those, but I don't think we'll have a chance in class to do that. The question is, do you remove the seniors that choose not to take the final from the top 15%? So you can fall into both categories and still be exempt from the final, or if you fall into either category, then you don't have to take the exam. Okay, so where we ended was talking about the laser and how it works. The most key element about understanding a laser is that emission is just as probable as absorption. Usually it is less common because we don't have as many molecules or atoms in excited states. But if we're clever and can get a population inversion, so we have more molecules in an upper state than a lower state, then we can get lasing, basically stimulating emission. And so here's an example of a molecule or an atom in an upper state. And this diagram isn't quite right. It says ground level. This typically would not be a ground level. It might be some other excited level at a lower energy that you're doing. But when you shine a photon in, as always, you could have absorption going from the lower state to the upper state. But if you have more molecules in the upper state, you're going to have more molecules falling back down and you're getting stimulated emission. So one photon winds up with 2. It's still conservation of energy that you have. So you start with excess energy in the upper state. You come in with an energy h nu. the upper state loses another energy amount, h nu, and you get 2 photons out. Now, the really important thing is, and this diagram kind of shows it, is that these 2 photons are exactly in phase with each other. So they're not only of the same frequency, but their waves are exactly on top of each other. So the amplitude plus minus in your electromagnetic wave is coming through at the same time. Important point about a laser is, I pointed this out last time, you have to optically design it so you enhance the correct wavelengths, correct frequencies that you have for your system. Someone asks what page of the lecture notes this is. Someone else says 237. So I guess we got that answered. Okay, so those 2 key things, you have to get the population inversion, and then you have to design your laser cavity to enhance the correct frequencies of lasers. And so where we stopped last time is I wanted to give you examples of how lasers work. And if you think about it, these are really pretty clever ways of doing it. So first laser we want to talk about was the carbon dioxide laser. This is actually a mixture primarily of nitrogen gas and CO2 gas. Nitrogen, like all diatomic molecules, has 1 vibration. It has a lot of rotational levels in that upper vibrational state. We can't excite the nitrogen directly by photons because there is no dipole moment change for the vibrational change, which you'd have to have. So we basically zap it with high electronic voltages, and we kick the molecule up into these upper states. And the reason we use nitrogen to build a CO2 laser is because a lot of its levels, the rotational levels up here, match quite closely the rotational levels in the excited state of the antisymmetric stretching vibration of carbon dioxide. So that's the vibration where one bond is stretching while the other bond is getting smaller. So the oxygens both move together in the same direction, and you'll notice that this does have a dipole moment change. Oxygens move to the left with a negative charge, carbon with a partial positive charge moves to the right. For this laser, then you design the optics so you can bring out some of these lines between the 2 vibrations, the lower level being the symmetric stretching vibration. Now notice the symmetric stretch does not have a dipole moment change. So this is basically one that you can't excite directly either, but you can have enhanced transitions coming down. So once you start getting some laser radiation or some emission coming out, we go back to our diagram here. 1 photon comes in, 2 photons come out. 2 photons pass through these molecules. Again, the 2 generate 4, 4 generates 8. And before you know it, you have jillions of photons, all in phase with each other and all actually in the same direction when you design your laser like this. The beams fly back and forth between these 2 reflecting mirrors, but we only allow 1 beam to come out at the end. And as I pointed out last time, notice we only let out about 1% of the radiation. So we get really immense energies within the laser tube, but we only let out a little bit to keep the stimulation of the laser going. Okay, well, let's look at another laser. And this is a better picture than what I had on the previous page, but the 2 pretty much complement each other. Just like in the carbon dioxide nitrogen case, the HeNe laser, helium neon laser, consists of 2 systems. Here they're atomic, one is helium, one is neon, that have closely matching quantum states. So here we get into some of the funny nomenclature of atomic levels, but basically we have helium with the configuration 1s2. It has 2 electrons, And we excite with electron collisions here, as you can see, one electron into an upper state. So I think on this diagram, yeah, you see we go from 1s2 in the ground state, and the electronic discharge can either create the 1s2s triplet state where the spins are in the same direction, or you can create the singlet state where the spins are in opposite directions. But the configuration is 1s2s. And why this is picked is because the neon has a higher s orbital where these energies match close enough. So when the helium atoms collide with the neon, then the energy goes into this S level. You then design your optics so that you can have a transition from this S level down to the P level. I've noted here that there are actually other transitions that you could try to look at, but this is how you design your optics so that light comes out in the red region, 632.8 nanometers, 15,802 wave numbers that you have. This, the last I heard, is still the common laser that's used in supermarket scanners. Again, the fact that it's monochromatic and the beams are in phase make it a very useful laser to have. Okay, so again, same picture here. So you can go from a 3s orbital down to a 2p orbital, or you can go from a 2s orbital down to the 2p orbital. This is primarily the singlet state, the 3s state, down to the 2p that we look at. But if you go to the triplet state and you have a collision, you could get something that would be, this would be in the infrared region at a lower frequency. Anyway, ultimately, the system, these photons lose more energy, they work their way back down into the ground state. But notice we don't try to get excitation in helium and then back down to the ground state. That would not work because you would not have a population inversion. Why you get a population inversion here is this 2p orbital of the neon is free to accept electrons. You could not have the lasing come down to the ground state because there would be lots and lots of neon atoms that are in their ground state. Okay, other lasers, I'll show you the diagram of an argon ion laser. This is pretty clever also. You can also do it with krypton. Maybe this is something that Superman might like since he was a big fan of kryptonite, I guess. Other comments, first major laser that was built was a ruby laser. And in case you didn't know, rubies are chromium plus 3 ions in aluminum oxide. This puts out light that you can barely see if you're lucky in the red region. It's sort of into the infrared at 694 nanometers. Bad joke, but the rumor has it that they quit making ruby lasers because the ladies protested that they thought there was better use for rubies in jewelry. Very common laser these days is a neodymium YAG. Neodymium ions, of course, are not very common. A lot of these rare elements we have to get from China. But the YAG stands for yttrium aluminum garnet. Yttrium is also not a very common element. But when you put this in there, then you can get lasing to come out. These lasers are excited by flash lamps. They're sort of like the lamps that used to be on old cameras when you had a flash go off when you took a picture. And so you put in a lot of light and get excited states, and then you get the lasing started. So let me see if I have pictures of these. Here's the argon ion laser. And this is a prettier picture of this laser cavity and laser tube that I talked about. The first lasers we got in my lab were argon ion lasers. They require 400 volts of electricity. So we had to have the university build special lines for us. We couldn't use 110 volt lines. So it had to be doubled twice, first to 220 and then basically to 440. This is called a plasma tube. And this has in it argon gas. But what's done in the lasing is we generate argon ions, and they are the ones that do the lasing. So pretty clever. And this could not have been done if people had not known exactly what the quantum states of argon ions were. So here's what happens. You apply a lot of voltage and discharge, drive the argon up to a high state. So I don't remember what electrons go where. Maybe you drive them from like a 3p orbital up to a 4d or something like that. But in any case, then you design the optics by having the correct distance between these two reflecting mirrors, such that you get radiation out at either 514 nanometers or 488 nanometers. 488 is a deep blue, 514 is a solid green color. So the optics define that, and then notice that we're coming to is this is an excited state of an argon ion. So we don't have any argon ions in the ground state to begin with. So any radiation that comes down to here, there's going to be a population inversion. So it takes deep knowledge to understand what these quantum states are. And here's a picture of the neodymium ion system. These term symbols won't mean much to you. The 4 up here in the superscript means it's a multiplicity. 2s plus 1 is equal to 4. So 2s is equal to 3, or s is equal to 3 halves, which means there are 3 unpaired electrons in this particular ionic state. But then transitions are generated between these different levels. The F and I tell you how much angular momentum there is. And since they're much higher than things we've talked about before, SPD, FGHI, you can tell that they're very high angular momentum states. But that's how you get 1064 nanometers out. That's about 10,000 wave numbers. Most of the time, you frequency double this. So you actually wind up at 532 nanometers, which is maybe 18,000 wave numbers. And often you even double it one more time to get into the ultraviolet. So there's lots of games you can play with these lasers. Okay, so again, here's my emphasis that these things could not have been done if there hadn't been a lot of prior knowledge, and you had to have a really good optical design, that you had highly reflecting mirrors. You had to have one mirror that transmitted 1% of the light as well as reflecting about 99% of the light. And you also had to have a terrific knowledge of the quantum states of these molecules and even the weird ions like neodymium and things like that. There's a bunch of stuff in your lecture notes. I encourage you to read them, but there were military attempts to use some of these lasers. I mentioned to you last time, the CO2 laser can be really powerful, but when you try to use it when you have clouds in the sky, then that can pretty much keep the military aspects from working and trying to shoot down ballistic missiles that might be coming. Here's a 250 to 300,000 watt laser. And so you can see the military is still trying to use some of these things. I mentioned to you last time that even if you take something like 100 milliwatts of light and shine it on a yellow pencil, you can start it burning. So you can figure out when you're getting a million times more energy like that, you can blow up just about anything. Okay, before we totally leave the topic of lasers and electronic transitions, kind of a neat kind of laser is called an excimer. And the military also used to love these kinds of lasers. But first I need to tell you what Xmers are. So back when we talked about homonuclear diatomic molecules, we learned to write the scheme 1s sigma squared, 1s sigma star squared for helium. It came out with a bond order of 0, and we all know you can't make helium dimers. Now, the interesting thing is you can make helium dimers in the excited state, and then it would be called an Xmer. So what you do is you take a chamber full of helium, and you zap it with, again, probably high voltages. So some of the helium atoms get kicked up to higher states. Instead of being 1s2, might be 1s2s or 1s2p or something like that. And then the excited helium collides with the normal helium, and you create an upper state of the helium, which we call the Xmer. This upper state has this configuration. Now notice this is at higher energy than the hoped for helium dimer here. Effectively, if we had the helium dimer, we would be exciting a 1s sigma star electron to a sigma orbital. So this would be the configuration. You count this up, you have 3 bonding electrons, 1 anti-bonding electron, you have a bond order of 1. So this molecule exists in the excited state. It doesn't last a very long amount of time, but when it degenerates, it gives off a bunch of energy. And every time, if you get the Xmer falling apart from the same state, it's always going to emit the same amount of energy. Delta E is equal to H nu. And so energy is released and H2 is dissociated. So I'm showing you this example since it's very easy to understand. No one has yet made a laser with helium Xmers. So that's sort of a false story. But, well, you can read what I stuck in your notes itself about Xmers. But what people have done is they've created molecules that you can't make in the ground state, like xenium chloride or krypton fluoride. You form these in an excited state. The excited state lasts about 10 nanoseconds, or about 10 to the minus 8 seconds, and then it releases powerful 308 nanometer light. And the way you do this is you start off with chlorine gas. You have to have a flow system. You run an electrical discharge to it. You create excited chlorine atoms. They collide with xenon. You form the xenon chloride in its excited state. When it dissociates, you get this laser light coming up. And these lasers can be extremely, extremely powerful, just almost unbelievable. I'm not sure, but I think the military may have given up on them for one good reason. They're terribly hard to manage. You have to have a flow system of chlorine. We actually had a professor who has now passed away, who worked with lasers, like krypton fluoride lasers. He had to have flowing fluorine gas, combining it with krypton. It all went in the chemical hood, but then the vapors went out through the roof of the outlet of the chemistry building. And I don't think that was too terrific for the environment, but anyway, he was able to run these experiments for a while. Anyway, just the fact that you have to keep flowing halogen gases to make these systems has made them a lot less popular. But I think it's really interesting if you look at the fact that you can build Xmers and get energy released like this. I'm trying to think of the fellow's name. The fellow that actually invented these lasers was a professor at the University of California, Berkeley. He went off to Ohio State, where he became their director of research. And something like 10 or 15 years ago, he was one of the finalists to become president of Texas A&M. I don't remember who got selected at the time. But anyway, so these are pretty neat. Okay, last comments about lasers. Many of the lasers, or almost all the lasers, are monochromatic, having a single frequency, but scientists and spectroscopists and other purposes, people want different frequencies than what the lasers put out. So you can use organic dyes to change the frequencies. You can use frequency doublers. These are typically crystals that we have to buy from China, made from various kinds of barium, boron crystals, if I remember correctly. You can use Raman, the Raman effect, to shift frequencies. Laser pointers are typically semiconductor lasers. They involve things like gallium arsenide. You can mix crystals to get frequencies added. And then here's a list of some things that can be done with lasers. I think, as probably all of you know, your DVRs and DVDs and all these run with a small solid state laser that's in these systems. So when you put in monochromatic light, the grooves or whatever that you have in your on your CD, or if you're trying to read barcodes, the monochromatic light is what you need to be able to make the computers read what you get out of it. We won't talk about photoelectron spectroscopy, but I just want to tell you that this is based on the photoelectric effect that Einstein got the Nobel Prize for. You all learned to do the problem that if you put h nu energy in, you would get an energy of the kinetic energy of the electrons coming out. If you took the difference, then you could learn what the ionization potential would be for a particular system. So this is a way to identify things. It's particularly good for deciding if you have gold or uranium or platinum or metals that might be in ores or things like that. Okay, well, look at some pictures. I'm going to skip or go over these really rapidly, just because I want to make sure we finish talking about spectroscopy today. This sideways slide that I can't turn with my PDF reader, this is one I often like to show when I tell people about the research we've done. We do a lot of work in the electronic ground state, looking at infrared. Raman has different selection rules. You remember we go to virtual excited states. But then a lot of times we want to know what the electronic excited states are like, partly to maybe understand what the photochemistry is from electronic excited states. So you can get up here by doing electronic absorption. So these horizontal lines, which look like vertical slides in this figure, these are different vibrational levels in the electronic excited state. And so if we start with electronic transitions from the ground state, we can start from different vibrational levels, go to these levels up here, and try to figure out what the spectra look like. What we and others helped develop was a technique of laser-induced fluorescence, or FES, fluorescence excitation spectroscopy. We take molecules, we put them into a supersonic jet, traveling at about 3 times the speed of sound. They cool to about 10 degrees Kelvin, so almost all the transitions come from the lowest vibrational level here. And we tune the laser to get into upper levels here, and then this dark line indicates the output that comes out. I have a chat comment. All right, let me see if Control Shift works, as someone suggests.
Professor, you have to do it Control plus shift, and then the plus or minus key. So it's the 3 buttons there.
At the same time?
Yes. Yeah. Or
Okay.
when I do it in order of Control, then shift, then plus. but I'm not sure here.
Okay, it's not working for me. I had everything working, but somehow my PDF system quit working, and so I went to some other PDF source. So sorry about that, but we'll just kind of continue here. All right, so what this next diagram shows, again, sideways, this is the laboratory system that we had. This is an OPO, which stands for Optical Parametric Oscillator. It's a laser system based on the neodymium YAG that we talked about. And I can't really tell you how it works, but there are clever physicists that make it work. So they put out the radiation at 1064 nanometers, then they frequency double it to 532, and then they frequency double it again to 266. And then the OPO part allows you to tune the laser. We shoot the laser through a lens into a large vacuum chamber that has to be at a very high vacuum. And then we have a sample container here that has a nozzle on it. And this is kind of like a fuel injector on your automobiles. And we open it 20 times per second. And the laser is pulsed 20 times per second. So the pulses go together. The molecules come out at 10 degrees Kelvin because of the way it's set up. The supersonic effect takes them to really low temperatures. And then we collect the light with a photomultiplier. This is based on Einstein's photoelectric effect. Goes through an oscilloscope, a boxcar electronics. And, excuse me, we finally get a spectrum on the screen. So here's an example of a molecule we looked at. And what we were interested in was unusual pi-type bonding. And so all of you know about hydrogen bonding in water. What we were looking at here was the hydrogen bond into the benzene ring. And so we had already looked at this in the electronic ground state, and we wanted to see what would happen in the electronic excited state. Turns out that this molecule can have 4 different orientations depending on whether this 5-membered ring bends up and puckers towards the benzene ring with the OH pointing towards it, or if it's this way with the OH pointing away from it. The only way you can get hydrogen bonding is if the OH on the 5-membered ring is pointing this way, and also that you've had rotation about the OH group, so the hydrogen is pointing towards the benzene. So say this structure, that structure, that structure would not work. So when we took the spectra, you'll see a bunch of zeros. The big strong line is the hydrogen bonded molecule. This one, this zero, this zero, this zero. Those are the other conformations that we have. On my PDFs here, these aren't color coded, so I can't tell you which one is which, but we're able to get spectra from each of these forms of the molecule. And then all this stuff right here, these represent vibrations that we have of the molecule in the excited state. Well, I don't want to bore you with the details of that, but notice that you get this nice, clean spectrum there. And just to show you how much this jet-cooled technique does versus traditional ultraviolet absorption, at the top here is ultraviolet absorption spectra of another molecule with a benzene ring. And you can see you can have a very hard time of telling where the actual levels are. But when we do the fluorescence excitation, you see all of these bands here, they come, they originate from the vibrational ground state, and we're basically recording an infrared spectrum of the electronic excited state. And from that, we can tell what happens to the conformation of this molecule, which bonds get weaker, which get stronger, and so on. And finally, here's another example of work that we've done in our lab. This is for the electronic excited state of pyridine. Turns out pyridine is a very rich or very rigid molecule in the electronic ground state, but in the excited state, you excite one of the non-bonded electrons on the nitrogen. Remember, pyridine is a 6-membered ring with a nitrogen replacing one of the carbons. Otherwise, it looks a lot like benzene. So we excite a non-bonded electron into an antibonding orbital. The ring becomes a heck of a lot less rigid. And from this analysis, we're able to tell that the molecule has actually bent out of the plane a little bit and is no longer, in fact, totally planar that we have. Okay, so that finishes electronic spectroscopy. I actually got further than I expected, so I need to stop the share and get us into statistical mechanics. So hang on for just a minute, please. Okay, so up to now, we've been spending a lot of time worrying about what kind of energies molecules can have. And if we hadn't talked about all of that, we could now not talk about statistical mechanics. I think for chemical engineers, this ultimately should be the most important part of the course, because from this, you can understand in the future when you're running computer programs, spitting out thermodynamic properties for you, telling you things about molecules that computers can tell for you. It's all based on the concept of statistical mechanics. And so basically what we've seen up to now is there are two kinds of energy that we can have when we talk about molecular systems. The first kind is radiation, electromagnetic radiation. This is photons. And we've seen energy of a photon is E is equal to h nu. The other kind of energy we have is when we have molecules. It doesn't matter if you've got something like a barrel of ethanol. If it's at a particular temperature, that energy has to be in quantum states. Now, this is not the way normally people think about energy. We think of heat as something that just makes us warm, but heat is actually just molecules residing in typically vibrational quantum states. So in our discussion of statistical mechanics, what we're essentially going to do is to look to see where the energy goes. If we want to put in 87 kilojoules per mole of energy, it just doesn't randomly go into a molecule. It has to go into specific quantum states. Now, why this is going to be called statistical mechanics is we're going to use statistics to determine what is the likely population of molecules in all the different quantum states that the molecules might have. And keep in mind that if you're talking about a barrel of petroleum, for example, you've got jillions and jillions of molecules, maybe something like 10 to the 27th or 10 to the 30th molecules. And so if we figure out the most probable way that the energy that can go into these molecules, we'll have a very good understanding of how things work. So here's our picture. We're going to have quantum states that we know about. We're going to apply statistical principles And from that, we're going to learn about bulk properties, like what is the enthalpy, what is the entropy, things like that that you probably commonly used in chemical engineering. I'll go over this part more rapidly since we're short quite a few lectures this semester. But I want to just remind you about statistics, things that you already know about. Let's say you flip a coin, and conventionally we say one side is a head, the other side is a tail. If you flip it, then you're not cheating. You have one chance out of two probability of getting heads. If you flip it twice, the probability of getting two heads is a half times a half. Or if you actually analyze it, that's because the probabilities of two flips are two heads, a head and the tail, a tail and a head, or two tails. So you'd have a 50-50 chance of having one of each, 25% chance of two heads, 25% chance of two tails. If we flip it 3 times, then these are the 8 probabilities that you would have. And so you'd see there's one chance out of 8 of getting all heads. And if you counted how many you'd have of getting 2 heads, there's one here. There should be, okay, this one is 2 heads also. So 2 chances out of 8 or 1 chance out of 4 of getting 2 heads and so on. So I think statistics like that is a lot of common sense. If you play cards and you have 4 suits of cards, the probability of drawing a spade is 1 out of 4. After you've taken out one of the spades, the probability of drawing the second spade is 12 out of 51. Third spade would be 11 out of 50. Chances of drawing 3 spades in a row comes out to be, I guess that's about 1 chance in 85, or as I've said here, 1 chance in 78, I guess. So not much chance that you'd ever do it. If you randomly pick any suit in a row, you wouldn't have to have the 1/4 in there in the first, so you just take the second 2 numbers in there. Okay, so how is this going to relate to quantum mechanics and statistical mechanics? And the best way for us is to look at a model of putting balls into boxes. When we start talking about molecules, they're going to be like balls, and then the quantum states are going to be like boxes. So we're going to see for each molecule which quantum state it goes into. But to do it on a simple basis, I'm going to take just 2 boxes. Later on, this might be just 2 quantum states. And we have 3 molecules that can go into these 2 boxes, or three balls that go into these 2 boxes. So here are our possible distributions. A, B, and C are all in 1. A, B, and C are all in 2. There are 3 ways that we can have 2 balls in box 1, and then we'd only have 1 ball in box 2. And then there are 3 ways that we can put 2 balls into box 2. So there are 8 possible configurations for this distribution. Now, if the balls are identical, and that's going to be our assumption when we start talking about molecules, we might deal with a mole of ethane, for example. We're going to assume all the molecules are the same. We really care about what is the probability of having 2 molecules in box 1 or 2 molecules in box 2. If the balls are identical, we can only distinguish by the number of balls in each box. So this is the kind of nomenclature we might use. N1 is the number of balls in box 1. N2 is the number of balls in box 2. So 3, 0 means 3 in box 1, 0 in box 2. But we saw on the previous page, there's only one way of doing this. Configuration 0, 3, 0 balls in box 1, 3 balls in box 2, only one way of doing it. But there were 3 ways of putting 2 balls into box 1, or 3 ways of putting 2 balls into box 2. So here are the 3 ways for box 1, here are the 3 ways for box 2. Okay, so there are only 4 kinds of configurations then that we can consider for this particular case. So our conclusion from this picture is if three identical balls could randomly fall into one of the two boxes, the weight represents the likelihood of a distribution. So this is what we're going to call the weight. How many ways can you do this? I'm going to skip the bottom part, but if you go to Vegas, don't bet. Go to some of their shows. They have the greatest shows on earth. If you go see Cirque du Soleil, go to the Ka show, K-A, absolutely unbelievably fantastic. But if somehow you start playing craps, which you shouldn't, then here are odds of what you can show for different numbers. Okay, back to statistics. And you don't need a course in statistics to understand what we're going to talk about here, but we need one important formula that our statistician friends tell us. And this is the general expression for the weight of a distribution. We're later going to apply this to trying to figure out what are the most probable ways that molecules go into quantum states. But for example, here we can think of this balls going into boxes. So capital W is large, and we're going to say there can be many different quantum states. The first one we number as N1, then the next one N2, then 3. There could be lots and lots and lots of these, and finally we end in N sub I. We might have 10 to the 24th different quantum states, and maybe 10 to the 30th molecules that we're putting into them. Anyway, the weight of a distribution, which we're going to want to maximize and get the most probable distribution, it's going to be capital N factorial. N is the total number of balls or molecules that we're talking about. And then we divide it by the product of the factorials of the individual populations, N1 factorial, N2 factorial, N3 factorial, and so on. In case you're thinking ahead, you might be thinking, how in the world do I take a factorial of 10 to the 23rd? And even if you have the fanciest handheld calculator, it probably won't calculate that number for you. But we're going to find schemes to be able to do that. Okay, so this is the formula we're going to apply lots of times. So let's see how this works for our case. We had 3 balls. If we want to look at the probability of the configuration, N1 equal to 3, N2 equal to 0. Numerator becomes 3 factorial. Denominator is 3 factorial times 0 factorial. 0 factorial by definition is 1. So we wind up with 3 times 2 times 1, or 6 over 3 times 2. And 6, this comes out to be 1. And we saw there's only one way out of the 8 possible ways that we could come up with this distribution 3, 0. If we want to look at the distribution 2, 1, then it's 3 factorial over 2 factorial and also over 1 factorial. So that's just 6 divided by 2, comes out to be 3. And we saw that there were 3 ways that we could have this distribution. So let me check the chat questions again. Okay, people are advising people on how to do things on craps, but okay, you can get some clues from that. But again, just do it for fun, don't do it for money. Okay, so again, this is the important formula that, again, we're going to use many, many times. I won't have time today, but next time that we meet, I'll probably just take a simple case where we might have 6 quantum states and 4 or 5 molecules, and we can see what kind of distributions that we get. But here is the crux of what statistical mechanics is going to be all about. We're going to start off and say that we know the total energy that we want to put into a system. How many calories are we going to put in? And we're going to have a total of capital N molecules. If we know how many kilograms of something we have, if we'll know how many moles we're going to have of that material, and then we can figure out where to put the energy into a particular system. Now, the energy, of course, is going to be dictated quite a bit by what is the temperature that we're starting from. And so temperature is going to be a vital element in trying to work this out. But the other thing that's going to be really important is what are the quantum states? And I've already given you formulas for calculating the populations of quantum states. We'll see where those formulas come from, but we'll see how that all applies into trying to put energy into these different quantum states. Well, we've run out of time. Again, if you signed in a little bit late, I've sent you a grade distribution. Your grades should be available on eCampus. If you have any questions about the grading, contact Dallas first. He didn't grade all the problems, but if you send him a question on one that Connor graded, he'll pass it on to Connor. If you're not happy with a resolution from one of the graders, go ahead and email me and I'll look to see if any adjustments need to be made about the grading. Someone asks, how will we determine who has an A in the class? Like if a student gets 2 A's and a B on an exam, what will that mean for the overall grade? The grade will be dictated by points. So you have points for the first exam, you have points for the second exam, you have points for your problem sets, and you have points for attendance. After you've taken your third exam, we will add all those points together, and I will come up with a curve for where you stand after 3 exams. If you tuned in late also, about 15% of the class will not have to take the final and will get their A's. That's the top 15% of the scores. Also, graduating seniors will not be required to take the final if you're content with whatever grade you have. So it could be an A, B, or C. If you have a D or F, please take the final and improve your grade. People ask about the attendance. The attendance is based on your attendance to Zoom sessions. To get full attendance credits, you don't have to attend all the classes. You'll be allowed to miss some and still get full credit. Beyond that, you'll get a percentage of what you might have attended. So maybe we'd expect you to have attended 30 or 35 classes, and if you attended 25 out of 30, you'd get 5/6 of the points, for example. Okay, well, stay healthy, work hard, have fun.